Hey, bro,
To be fair, he's the one who showed me that, but when he first did it, I like,
Also, why was they asking me to start a group? And then first of all, you're like a little child. Second of all.
All right, so we're going to talk about arc length and curvature. And we're going to, the reason we're talking about arc length is that we're going to use arc length as our entry point into talking about curvature. And we'll talk about why that is in a little bit. All right, so when we talked about parametric equations, we went through an argument. So I'm going to say just a two-dimensional argument. X is some function of t, and y is some other function of t. We said the arc length on some interval, a to b, where the curve didn't cross itself in that interval. S was this nice integral from a to b of the square root of x prime of t squared plus y prime of t squared. dt. So we went through an argument of why that was the case. Very similar to our arc length formula for an explicit function. For an explicit function, we have the square root of 1 plus f prime squared dx. Similarly, for vector valued functions, for a curve, represented by, we're just going to jump straight to 3 dimensions, by r of t is x of t I hat plus y of t j hat plus z of t k hat. We know that we can think of these components as parametric equations that describe our curve. So our arc length along this curve on a to b is S is going to be given by a to b, the square root of, we just have 3 terms. X prime, I'm going to leave off the t dependence, y prime squared, and z prime squared. dt. Well, for this vector valued function, what does this quantity, the square root of x prime squared plus y prime squared plus z prime squared, it's the speed of, if we think of a particle moving on the curve, it's the speed. So what we can say is the magnitude of r prime. And what we're going to write is that S is the integral from a to b of the magnitude of r prime of t dt. And we're saying that this is, our conditions are, we're talking about a smooth curve on a to b. And it's not crossing itself anywhere in the interval. So this is how we're going to represent the arc length of a vector valued function. So you might be asked a question that involves finding the arc length. This is how we're going to find the arc length. And as you might expect, because of this quantity, those arc length integrals sometimes are interesting integrals. that take a little bit of work.
Oh, good.
But the nice part is that they're definite integrals, so
Good.
that makes them a little nicer. We're going to use this to develop the idea of curvature. And the reason, just a little background, the reason that we use arc length to talk about curvature is we want curvature to be a property of the curve, not a property of how we parameterize it. And arc length is a property of the curve. It doesn't matter how we parameterize a curve, the arc length from one point to another point should be the same, regardless of how we parameterize it. Well, the curvature should be something that's a property of the curve, not a property of the parameterization. So that's one reason that we use arc length to get to the idea of curvature. All right. So let's start talking about this idea of curvature. It might seem a little counterintuitive to talk about curvature in terms of arc length, but it turns out it's really nice. All right, let me draw a picture of some arbitrary curve in space. So there's our curve. And I'm going to say that this is, we're going to define some starting point as t equals a. We might say t equals 0. And we're going to go to some arbitrary time t. And from here to here, this is the arc length along the curve. So if we think of arc length as a function of time, and we have some starting time, can we agree that if we have a specific arc length, if we talk about a specific arc length, that defines a unique point on the curve? If we say this is, let's say, t equals 0. We say that point is t equals 0, and we say if we're at arc length 5, that's a unique point on the curve. Can we agree to that? Yeah. So a specific value if s is a function of t, each arc length gives a unique point on the curve. So we can say that the arc length, s as a function of t, is going to be the integral from a to t of the magnitude of r of u is just a dummy variable for integration, du. Sorry, r prime, yes. So our arc length as a function of time is this integral. And so we're going to call this the arc length function. This integral is the arc length function. That is the function that gives us an arc length on the curve. Yes?
Why is it r prime?
We said the arc length, so back here,
I know, but like, so back there, why is it r prime?
because when we related it back to when we talked about parametric equations, that the arc length on on a curve is x prime squared plus y prime squared.
Oh.
And so we just added one component, x prime squared plus y prime squared plus z prime squared square root. And that is the same as the magnitude of r prime. Okay. All right, so this integral is the arc length function, and S is the arc length parameter. So the integral is our arc length function, and S is the arc length parameter. So this gives us a way of parameterizing a curve in terms of the arc length. So instead of having x be a function of t, y be a function of t, and z be a function of t, we can have x be a function of the arc length, y be a function of the arc length, and z be a function of the arc length, because each arc length gives us a point on the curve. So we can parameterize the curve, a curve, in terms of arc length. So I'm going to go over here. And the reason we want to parameterize the curve in terms of arc length is because arc length is a property of the curve, not a property of the parameter. And each value of S, like we said, is going to determine a point on a curve, an x, y, and a z. All right. So what we're going to do, so now we have a method of parameterizing a curve in terms of arc length. Because my arc length parameter is this integral. By the fundamental theorem of calculus. We can say that ds dt equals magnitude of r prime. The rate of change of arc length with respect to time is the speed of an object moving on the curve. So this is going to be a key piece of information, that the rate of change of the arc length with respect to time is the same as the speed of a particle, an object moving along the curve. All right, so that's the other piece of information that we need for curvature. This is going to be key to our talking about curvature. All right, so we use the arc length parameter. We end up using the arc length parameter to define a quantity for curvature. So let's talk intuitively about curvature for a second. So are we good with this idea? This was the main thing we were trying to get out here, was the speed of the object on the curve, arc magnitude of r prime, is the rate of the change of arc length with respect to time. All right, so I'm going to draw some circles. Let me undo that one. I want to move over. I want to make that one big. That one smaller. And that one smaller. Which of these curves has the greatest curvature?
Question.
All the same.
Same curvature?
Symmetrical.
Which of these are more? Which is closer to being flat?
They're all equally close to being flat. The small
What if I had a giant circle? An arc along a giant circle
Well, like
isn't?
we said, the Earth was flat because it's close enough to being flat.
No, we're not talking about the Earth anymore. We're not talking about anything. Oh, the big one's most flat. This is least curved.
Yeah, of course.
This one's closer to being flat. If we had a giant circle, that's why we can say that we said we can approximate the Earth as being flat, because the Earth is a pretty big sphere. So this is more curved. And this is even more curved. So based on this observation, how do we expect curvature and radius to be related?
The smaller the radius, the greater the curvature.
So we should have an inverse relationship. So we expect an inverse relationship between curvature and radius. And thinking about a particle moving on these paths, what other quantity that we've been talking about do we expect curvature to be related to?
How fast the radius.
What we've been talking about when we talk about velocity and acceleration. The normal component of acceleration. That tells us how much we're turning. That gives us the normal component of acceleration turns us on the curve. So we expect curvature and a sub n to be related. So we expect the normal component of acceleration to tell us something about how we're curving along a path. All right, so that's our intuitive ideas about how, if we quantify curvature, how things should come out. So let me draw a couple more pictures now. So this is our intuition. A couple more pictures. I'm going to draw 2 pictures of a curve, because I'm going to put some illustrations. Those are the same curve. And I'm going to call that A, and I'm going to call this point B.
Are they supposed to be like the same?
They are the same. They are the same curve. Same curve. So I'm defining them to be the same. All right. So thinking back to what we've been talking about for the last several days: velocity, acceleration, tangent vectors, normal vectors. What quantity that we've been talking about that we can quantify on a curve is changing more at B than A? A sub n is changing more. So let's go back one step. What's a little easier to calculate than the normal component? Tangential component. So the tangential component is in the direction of the unit tangent vector, right? So I'm going to say this blue vector that I'm drawing on here is, the blue vector that I'm drawing on here, that is going to be my unit tangent vector. And I'm going to put some unit tangent vectors on this curve. So here's one here, here's one here, here's one here, along there. But then here we get doing this, and then doing that, and then doing that, and then doing that, and then doing that,
They're getting further away.
and then doing that. So those are some unit tangent vectors. the tangent, unit tangent vector is changing direction more at B than A. Oops, that's not. Why did I do that? That's what I wanted. T is changing direction at B more than A. So motivated by that, because the unit tangent vector is relatively easy to calculate. And the unit tangent vector, thinking back to what we just talked about in terms of arc length, is related to what?
The speed.
Isn't it related to don't we find the unit tangent vector by finding r prime?
Yeah.
So unit tangent vector is related to r prime. So that's a good thing. Motivated by this, we're going to define the curvature. K, curvature. Curvature with a K. Curvature. But C is the speed of light, so we couldn't say C. And C is a constant. See, sounds more like curvature. K equals, we're going to say it's the magnitude of the rate of change of the unit tangent vector with respect to arc length. And we're going to say that this, we could also write this as T prime of S. And we're talking about a smooth curve. So we have a smooth curve given by R of S. So let me emphasize that. The curvature, we're defining the curvature as the rate of change of the unit tangent vector with respect to arc length. The tangent vector with respect to a specific arc length here where the curve is more curved is changing more quickly than the unit tangent vector with respect to arc length is changing at A. And then we're going to define the radius of curvature we expected an inverse relationship, so we're going to say R equals 1 over K. And just say that's our radius of curvature. Now, what we hope by making these our definitions is that nice things come out. If we calculated the curvature of a circle and then found R, the radius of curvature, we should expect that to be the radius of the circle. So, and it turns out, and we'll see that when we do a few things, it turns out that this definition does work out the way we want it to. So that's part of what you do in math, is you define something one way, and then say, well, does this definition make sense in terms of what things we already know? And it turns out these definitions do. So the curvature of a curve is the rate of change of the unit tangent vector with respect to arc length. Now, in general, parameterizing a curve in terms of arc length is not easy. Because that arc length function, that integral, the square root of r prime, magnitude of r prime, that's your arc length parameter. And then you have to have x in terms of that parameter, y in terms of that parameter, z in terms of that parameter. In general, it's not easy. So what we want to do, generally, we want to express the curvature in terms of our original parameter. So that's what we're going to do next. This is our definition. We don't want to have to calculate with this definition. We want to calculate with our original parameter. Calculate with t. Calculate with theta. That's how we parameterize our curve. All right, so let's do that. So we want curvature in terms of our original parameter. All right, so we have that k is the magnitude of dt ds. That's our definition. By the chain rule, dt ds, magnitude of dt ds, equals the magnitude of dt dt times dt ds. And I can write that, you might be able to see where we're going here, as dt dt over ds dt. And dt dt is just the magnitude of t prime. And ds dt is magnitude of r prime.
Wow, that's a full circle.
There's our arc length. We use a fundamental theorem of calculus on our arc length function to get this. And we have that k equals the magnitude of t prime over the magnitude of r prime. Well, we know from what we did before that a sub n is the magnitude of r prime times the magnitude of t prime, right? That's it. When we first came, we differentiated our acceleration, and this was our normal component of acceleration. And that we decided, I did a video we could figure out when we did a few other quantities. This was the magnitude of r prime cross r double prime, v cross a, over the magnitude of v, or r prime. So t prime magnitude is the magnitude of r prime cross r double prime over the magnitude of r prime squared. We're going to substitute that in here. And finally, k, we're going to substitute this quantity for t prime, and we just have to divide by r prime again. Our curvature is the magnitude of r prime cross the magnitude of r double prime over the magnitude of r prime cubed.
Which one is?
What's that? This is going to be how we calculate curvature. R prime cross r double prime divided by r prime cubed.
So we don't have to use t.
We don't have to find the unit tangent vector. We don't have to parameterize our curve in terms of arc length.
But if for some reason we already have the unit tangent vector, we would use that.
If you had the unit tangent vector, you could definitely use that.
Step and use that.
Alright,
But remember, our unit tangent vector is r prime over the magnitude of r prime, so to find t prime sometimes is messy. So this is our curvature. This is how we're going to quantify our curvature of a curve.
But wait,
The curvature of
the radius of curvature is 1 over k.
Oh, I can't
Let's do r prime divided by the magnitude
Find
of
the
r
radius
prime
of
squared.
curvature.
Because we can't cancel this inside the cross product.
No, but t prime is t prime. Oh, God.
Yeah, it's t prime, right?
I got you.
Dylan!
Yeah, it'd be nice if it was just t.
That would be.
All right, so let's recap. We started by coming up with our arc length function. We came up with the fact that r prime, magnitude of r prime, is the rate of change of the arc length with respect to time. We defined our curvature as a rate of change of the unit tangent vector with respect to arc length, and then we get to here. So this is our quantification of curvature. What we're going to do on Friday, tomorrow, is we're going to take this definition of curvature and talk about acceleration and relate this back to some familiar ideas about acceleration that you might have learned as well. So, and I wanted to point out here, we made our, we expected our curvature to be related to our normal component of acceleration, and that's our we used our normal component of acceleration to get this quantity.
Is that R double prime on the bottom or just
R prime, because we have all these R primes in the denominators here. R prime, R prime, R prime, R prime.
So it's,
Yes.
it's easier to do that last equation than like the one like a couple steps before the
Here?
calculating
it's a little
t.
Well, so t is, remember, t is r prime over the magnitude of r prime. So then to find t prime, you have that ratio, that quotient
Say
with a
quotient rule.
with a quotient rule, and you have a radical in the denominator. So usually calculating t prime is messy, because we want to try to avoid, that's just like we wanted to avoid calculating the unit normal vector by doing t prime over the magnitude of t prime. So that's why we want to avoid that. So we just, all we need to know is about our r prime, our double prime, and those quantities. And those are usually, for a nice curve, those are relatively easy to calculate. So we have nice derivatives, nice cross product, magnitudes, all this nice vector stuff comes together for curvature. So I just want to go through one example of calculating a curvature, and then we'll be done for today.
How long is this example?
How long are these going to be?
Not too long. We're just calculating. It might fit in that space. You could probably make it fit in that space if you use the horizontal space well.
Why do we use the I-hat? So now I have even more incentive to not use the I hat, J hat, K hat method, so you don't have to
Right.
use all the K.
All right. So we want to find curvature.
I have these 4 lines.
Just like take
And just so you know, some textbooks will use rho for radius of curvature. We just use an r. All right. So we've defined our curvature. We need r prime and we need r double prime. Wait, let's think about this for a second though. What kind of curve is this?
circle,
3rd dimensional.
parabola, parabola. So I'll go with
So we get a parabola. If we project it into the xy plane, we get a parabola. If we project it into the yz plane, we get a parabola. But in the xz plane, it's a line. So what it is it's a parabola that's kind of, let's see if I can. It goes like this, up. There's my line, and then it curves around, but it keeps going up.
Oh.
So it's like the side of a mountain, and you're going around the edge of the mountain. You're like a switchback. So you continue going up, but if you project that switchback, if you look straight down the side of the hill, it would look just like a line.
Wow.
I do not.
You should make that.
I would, yeah. We looked at an example sort of like that, where we did a matching thing right at the beginning. There's kind of a parabola that kind of climbs
Oh,
up
yeah,
like that. Yeah. So we get the parabolas projected in two dimensions, but if we look straight down the side of the mountain, it looks like a line. Yeah, the switchback. That's a good analogy. R prime of t. Nice easy derivatives. Here, how about we write it like this? We'll write it like that. That'll make it even smaller. Take up less room on your.
God bless you, sir.
R double prime. We need R double prime. For 1.
No, it's 401.
Oh, 401. I forgot my. Magnitude of R prime is the square root of 16 t squared plus 1 plus t squared. So the square root of 17 t squared plus 1. Magnitude of R prime cubed. We need that for our denominator, is 17 t squared plus 1 to the 3/2. We need R prime cross R double prime. So we're going to have our determinant I, J, K, 4t1, T, 401. When I do that cross product, I get I minus 4k hat. So the magnitude is just the square root of 17. So 1 squared plus 4 squared. So k is the square root of 17 over 17 t squared plus 1 to the 3/2.
What does that even mean?
That's the curvature.
So if this, and let's think about if this makes sense. If we have a parabola, what do we expect the curvature of the parabola to be as we get out closer to the ends of the parabola? It should be 0, right? It should be about flat as t approaches infinity.
Oh, yes, really.
This approaches 0.
Nice work, Jake.
Nice work.
And where would we expect the maximum curvature to be? At the vertex, right? And where would that be?
0.
T equals 0. That's what makes the denominator the
The smallest it
smallest it can be.
Nice.
Yeah. So that's the vertex of the parabola. Or parabola x y equals x squared. No, x squared equals y, etc. All right. Questions. So this corresponds to our intuition about how the curvature should work on that curve. We'll talk tomorrow about how we'll show that the curvature corresponds to our intuition about other things that have to do with things curving. All right. So it